let's move on to our next speaker. So if Shamit is here.
Yeah, should I share?
Yeah, go ahead.
Okay, and can you see my my talk?
We can see the slides. That looks good.
Super. Okay. So
I'm
very
sorry.
Go ahead.
Our final speaker today is Shamit Kachru from Stanford, and he'll be telling us about two different ways to get explicit K3 metrics from string theory. Thanks.
Okay, thank you. So I'm happy to virtually be here. I've never been to Nankai, and I guess I still haven't. So I'm going to talk about K3 metrics in string theory. To the extent that I say anything new, it will be based on work with Arnav Tripathi and Max Shamit that appeared in those two papers. I should say that the second paper finished this subject from a point of view of physical. The certain amount of physical insight was obtained, but a lot of work remains to turn it into rigorous mathematics by the standards of analysis, and Max and Arnav are really pushing that forward, and I'll mention a little bit about what they're doing by the end. But I've been busy doing other things. Okay, so what is the subject? Well, the Calabi conjecture from the 50s stated that there is a unique Ritchie-flat Kähler metric on a Kähler manifold that satisfies a relatively mild topological condition of vanishing first Turing class for each choice of the cohomology class of the Kähler fold. And this theorem was proved 25 years later or so by Yao, actually when he was at Stanford. Now, this result has been amazingly useful, but it is famously non-constructive. And largely the usefulness comes from the fact that this condition of vanishing first Turing class is very easy to check using algebra geometric techniques. Now, why is this of interest to physicists? I'm a physicist. Well, here's a schematic picture of the sort of space of M theory and string theories that exist in 10 and 11 dimensions. And all of these, because they exist in higher dimensions, need to be reduced to lower dimensions to get physics of any interest to most physicists. Now, string theorists are interested in Calabi-Yau spaces then, because in considering reduction of these theories, you need to satisfy the Einstein equations, and the vacuum Einstein equations give Ritchie flatness as one of their conditions. So these spaces, conjectured to exist by Calabi and proved to exist by Yau, give examples of vacuum solutions of string theory. But more generally, they also play a central role in various considerations arising in string duality, which is now, almost a subject in math, and also in differential geometry and in algebraic geometry. And that's really my interest at this point, not so much physical application. So today what I'm going to do is describe some sort of conceptually new approaches to the problem of understanding these metrics, the Calabi-Yau metrics, in a Goldilocks example of such a space. Remember, Goldilocks had this pickiness. There are some things that are too hot and some are too cold and some are just right. Well, with Calabi-Yaus in 2 dimensions, there's just the torus and it's not so interesting. In 6 dimensions, we have Calabi-Yau threefolds or 3 complex dimensions. They're a little too hard for us to understand the metrics at this point, though progress occurs. But in dimension 4, there is a sort of simplest example of a non-trivial compact Calabi-Yau, the K3 surface. It plays a rather central role in various pieces of duality. And so it's interesting, but it's not trivial. No one's been able to write down closed formulas for metrics. So I'm going to attack this problem of finding the Ritchie flat metric of K3. And I'll do this in a way that's broadly familiar to experts in field theory duality. So let me sort of describe the qualitative idea. So what do I mean by duality? First of all, we were told to make these talks accessible. So I've tried to make at least the big picture accessible. Duality is what occurs when there are 2 views of essentially the same object. And what is the point of having 2 views of the same object? Well, the point is that from each point of view, different aspects of the object may be made manifest. So this is an artist's conception of Wittgenstein's rabbit, which is an object that, depending on how you view it, can be seen as either it's a rabbit along the vertical axis and a duck along the horizontal axis, and maybe different aspects of the creature are clearer from one perspective or the other. Okay. So here, although the basic subject that we're going to study is string theory on K3, the objects in which we're going to study the duality are derived from it, but are smaller objects. They're going to be 2 dual low energy quantum field theories that don't have any gravity in them. And the object that we're going to get a dual view of isn't so much the whole quantum field theory as one of its basic properties, the moduli space of vacua. Okay, so here we have the picture of maybe the most famous moduli space of vacua that occurs. If you have spontaneous symmetry breaking in a theory of a complex scalar, then, famously with a negative mass term and a positive quartic, you get a circle of vacua parameterized by Goldstone boson. So that could be a sort of trivial example of a moduli space. The theories we'll consider have more non-trivial moduli spaces of low energy or zero energy states, and we'll get dual views of these moduli spaces, and that will sort of be our trick. Now, in our case, of course, we're not just interested in general dualities, we're interested in metrics on K3. That was my start. So importantly, we will want the moduli spaces of vacua on which we obtain dual views to be K3 itself, the K3 surface, with the induced metric being the Ricci flat metric, not some other, K3 of course admits many other types of metrics as well. So what are the two pictures? If we're going to have a duality, right, just like in this picture of the Drabbit, we need to have sort of two axes from which to view the object. Well, the two pictures will correspond to sort of pictures of which moduli space in the field theory is giving us the K3 surface. So in the first picture, we will obtain K3 as a Coulomb branch for those who know what that is. We will have a brane of the string theory, a D3 brane, probing the K3 surface in type 2B string theory or in F theory, which Mboyo was just talking about. Okay, so the Calabi out there is K3, the D brane sits at a point and is moving around. And sort of obviously, if the D brane can move around on the entire K3 surface, its moduli space includes as a component the K3 surface itself. There are going to be some important technical details in this picture. The D3 will have to wrap an additional circle, and there will be a dual picture of it as something called a little string, which is a slightly larger object than a quantum field theory, compactified on a T3, though we'll just use the low energy field theory limit. Now, there's a second picture, a dual picture. This involves, instead of a D3 brane, a D2 brane in type 2A string theory, transverse to the K3. And in this picture, in the D3 picture, the K3 surface is a Coulomb branch in the standard language of quantum field theory. In the D2 picture, it turns out that the K3 surface is a Higgs branch. And that gives some important advantages because in theories with the relevant amount of supersymmetry for these D branes, there are non-renormalization theorems that govern Higgs branches that don't govern Coulomb branches. Okay, so there are two sides in our duality. There's a Coulomb side and a Higgs side. The physics is that of, well, there's this D3 brane transverse to K3 on, in the picture I just talked about, but really it's a higher dimensional little string compactified on a torus. The dual side is a D2 brane probe where the theory is arising on a Higgs branch. The metric on K3 arises in two different ways. In the Higgs side, it's purely classical. A non-renormalization theorem tells you the metric on moduli space can't receive any coupling constant dependent corrections. And so if you can compute the classical metric, you're done. In the Coulomb side, on the other hand, quantum corrections can famously correct Coulomb branch metrics. This goes back in terms of computation to loop computations in the 80s, and then the work of Seiberg and Witten giving exact results. And the way that arises in string theory is that there's a sort of classical metric on the Coulomb branch, there's a one loop correction, they're instantons, and those get translated in the string picture to algebrogeometric objects, disk instantons that wrap various cycles in K3. Okay, and the big tool that lets you attack that side were you to be so brave as to proceed directly is a formalism developed by Gayatto, Moore, and Knightsky, which I'll very, very telegraphically talk about. And the reason I'll only telegraphically talk about it, though we go into much more detail in our papers, is because the Higgs side is much more powerful. The results are classical. There is a hyperkähler quotient construction of the K3 metric. And this sort of ties to an old Hitchin question, could you realize K3 is an infinite dimensional hyperkähler quotient? So my claim will be the answer is yes. And it sums up all the answers required for the GMM formalism on the dual side. Okay, so to get there, I first need to discuss the theories on these branes and their moduli spaces. So let's go back again to some sort of basic statements. One of the discoveries of the mid-90s, the first duality revolution, was a zoo of novel theories not previously expected to exist. Okay, namely field theories in 5 and higher dimensions, 5 and 6 in particular. The main tool of discovery was the study of low energy theories on D branes or more general branes, and S branes also embedded in the full 10-dimensional string theory, but studied in a low energy decoupling limit. Okay, so the fundamental example, perhaps the most famous, is a 6-dimensional theory that has chiral supersymmetry. The maximal supersymmetry accessible for a theory in that number of dimensions involves 16 supercharges. There are 2 versions of it, and this version has 2, 0, so it has chiral supersymmetry. One way to get it is on NS5 branes in type 2A string theory. But we're not going to be interested in the 6-dimensional theory. We will be interested in its compactifications all the way down to 2 + 1 dimensions. Let's start by first compactifying on a 2 torus. On a 2 torus, it gives rise to a theory that looks at low energy like a U1 gauge theory. What is the moduli space of that? Well, sort of not surprisingly, if you consider the analogs of Wilson lines of the tensor field that exists on NS5 branes, you get a Coulomb branch moduli space that is the dual of the mirror torus. So it's basically another torus. And actually, you know, this way of compactifying 5 branes on a 2 torus also yields theories with 16 supercharges in 4 dimensions. And the SL2Z that acts naturally on 2 tori translates into the S duality of those theories in 4 dimensions. But in any case, for us, the interesting fact is that the Coulomb branch moduli space of the 2-0 theory on a torus is itself a torus. Now, if you added an additional circle, so now you compactify a T2 times a circle, you would get 2 additional scalars in the low energy theory. There was already an abelian gauge field in 4 dimensions. It gives a Wilson line on the circle. You can integrate a mu along the circle. And that's a periodic scalar in the 2 + 1 dimensional theory. So now you have 3 scalars, the 2 that span the torus moduli space in 4 dimensions in this Wilson line. And you also have a 3D photon. But in 3 dimensions, a gauge field, an abelian gauge field, has 1 degree of freedom that can be dualized to a scalar using the epsilon tensor, right? So you say this field strength F mu nu is just epsilon times d phi, and that gives rise to another scalar field. So it looks like you now have 4 scalar fields. And from the M theory picture of this same physics, you can quickly see that this theory has a moduli space that's given by a 4 torus, okay, which is not a big surprise. So the photon and the Wilson line give another 2 torus that sort of fiber trivially over the 4-dimensional torus moduli space. Okay, now why am I reviewing that? That's a way to get a 4 torus as a moduli space of some kind of low energy field theory. And I reviewed that because, not so much because I'm interested in the 4 torus, I think we know a lot about the 4 torus, but we're going to use an analogous but more complicated system where there's a theory whose moduli space is K3, which we're interested in. Okay, so here's a theory that has a K3 surface as the moduli space. The theory we were just talking about is maximally supersymmetric in the sense of field theories. It has 16 supercharges, or the equivalent of 4dn = 4 supersymmetry. The one that we're going to be interested in will be half as supersymmetric. K3 preserves half as much supersymmetry as T4. And in fact, it's going to be the first sort of 6-dimensional theory discovered that has the equivalent of 4dn = 2 supersymmetry. Okay, so what are the salient properties of this theory? Well, first of all, it will again arise on NS5 branes in 6 dimensions, but now in the heterotic string instead of the type 2 string, or equivalently, we can dualize and realize it on D5 branes in the type 1 string. There are different descriptions of this theory, as there often are in string dualities. One description, maybe the most convenient one that arises in the type 1 string, is as a 6D SU2 gauge theory with 16 doublet hypermultiplets and an SO32 global symmetry. And this is sort of easy to understand. The type 1 string has an SO32 gauge group, so it has 16 9 branes sitting in it. And the SU2 gauge theory with 16 doublets arises because a D5 next to those D9s has this spectrum. Okay, just from the open strings that stretch between the 5 and 9 branes. Now, when we compactify this theory on a 2 torus, it is a low energies, a theory that has a rank 1 Coulomb branch, but the Coulomb branch is compact, it's a sphere. And in fact, that sphere has 24 marked points on it. It's a dual object to this D3 brane that we started with, moving around in F theory on the base of an elliptic K3. An elliptic K3 can be viewed as an elliptic fibration over a P1 with 24 interesting points where the torus fiber degenerates. Generically, they can collide and give you more interesting singularities, of course. And so our Coulomb branch in this D3 picture consists of points on the P1, and where the marked points are, the 3 brane will come near an interesting 7 brane or collection of 7 branes, and you may get interesting matter. Okay, now let me let me switch pictures for a minute. So this is a Coulomb branch picture. It's sort of non-trivial. It's what arises naturally in the three-brain probe in F theory, and that system was studied, for instance, by Sen, and much physics was extracted from it, but it's complicated. Let me now discuss how hyperkähler metrics more generally arise on Coulomb branches. So let's leave the story we've been discussing for a minute. I'll come back to it and discuss generalities about 4D n equals 2 field theories. Okay, so there are two kinds of multiplets. There are vector multiplets that contain a complex scalar and some fermions in a gauge field. And then there are hypermultiplets, which consist of two chiral multiplets and conjugate representations of any gauge group and their Fermi partners. So the general structure of the moduli space of vacua, well, there can be Coulomb branches on which the fields, phi, the scalars and the vector multiplet, which are adjoints of the gauge group, get a vev. There can be Higgs branches where the chiral multiplets and a hypermultiplet get a vev, so Q and Q tilde get vevs. That generally, in most examples, Higgs is the gauge group. But there can also be mixed branches where part of the gauge structure survives, but some of the hypermultiplets have a vev. Now, I go through this because the geometry of these moduli spaces in 4D n equals 2 theories is different. The Coulomb branch spanned by these adjoint scalars phi is what's called a special Kähler manifold. It's naturally even dimensional, and it has a structure made famous, for instance, by Seiberg and Witten, though it dates back much further. The Higgs branch is a hyperkähler manifold. Now, on compactification to 3 dimensions, this changes in an important way. The Higgs branch remains hyperkähler. Scalars don't gain more components when you compactify on a circle. But the vector field of the 4D n equals 2 theory will give additional scalars in the way we described through its Wilson line and through dualization. And so the Coulomb branch becomes, instead of 2K dimensional, 4K dimensional. It becomes naturally, a multiple of 4. And in fact, you can show that it becomes hyperkähler. So how do you find the metric on the 4D and 3D Coulomb branch? Well, at each point on the 4D Coulomb branch, there's an effective low energy action. It has, for instance, the gauge fields with a gauge coupling E, has a theta angle. And this action sort of encodes and is encoded by an auxiliary Seiberg-Witten curve, which here is sort of a genus 1 surface whose complex structure is precisely displayed in the low energy action. So the gauge coupling, determines m tau, and the theta angle determines real tau, and the way everything's here. Okay. Now, if we reduce to 3D, what happens is that this torus, the genus 1 surface described here, actually becomes physical. It becomes visible in the physics. The action for the new scalar fields that span this torus is given by a term that corresponds to the Wilson line, sigma, and a term that comes from dualizing the gauge field, dB. Okay. So the result is a moduli space in 3 dimensions that's an elliptic fibration with elliptic fiber E over the old 4-dimensional Coulomb branch, and with an area that's determined by the radius of the circle. And after going through all the rescalings you need to do to take care of dimensions of gauge couplings and so forth, it turns out the volume of that elliptic fiber goes like the inverse radius of the circle. Okay. In the case of the D3 probe on elliptic K3, right, adding the circle that the D3 wraps and going to low energies sort of gives you a new 2-dimensional theory where the full K3 is visible as the moduli space instead of just the base P1. So the leading large R metric is given by combining the kinetic terms for the new scalars with those of the 4D Coulomb branch fields. And that metric is proposed to be the hyperkähler metric on the Coulomb branch. Okay, so at this stage, you could read off some trivial approximation by just combining that action with, with the action you already had given to you by Seiberg-Witten theory. But that's not an exact picture. Okay, so there are 3 sources of physical corrections to the naive classical picture. There's the 1-loop corrections and 4D instanton corrections that we know how to determine from Seiberg-Witten theory. But there are also new corrections that come from BPS states of the 4D theory. These are states that preserve some of the supercharges, particle states with some charges that preserve some supersymmetry. And that when you go to 3 dimensions can give new instantons by running around the circle, viewing it as a Euclidean time dimension. So there are new sources of corrections to the 3D metric. Now, going through the formalism to solve for the full kind of data that we then need, this set of instanton corrections, both in 4 and 3D, is beyond the scope of this talk. It's a short talk, but it combines classic work of the 90s with more recent work of Gayatro, Moranitsky. Now, if you're actually able to solve for the BPS spectrum at each point on the Coulomb branch, in 4 dimensions. So that's some set of degeneracies, omega, gamma, and u. U is a Coulomb branch point, gamma is a charge. So omega is some integer counting BPS states. Then the claim is you can reduce the determination of the hyperkähler metric in 3 dimensions to solving sort of an integral equation that's completely determined by those omegas. Okay, it can be solved by an iterative technique given these BPS counts. I don't have time in this talk to give the details. I did give details in a longer talk, which you can see there on YouTube, or you can look at the papers. But I'm instead going to talk for the rest of my 10 minutes about the Higgs branch formalism, because that's where we actually can make some hay, and then duality lets us, in fact, shed light on the other picture. Okay, so we got this far by studying the heterotic NS5 brane on a 3 torus. But famously, there's a duality. The heterotic string on T3 is the same as M theory on K3. A wrapped NS5 brane on T3, or equivalently that F theory 3 brane wrapped on a circle, is dual to a transverse M2 brane moving around on the K3. Now, we can further reduce the M theory side on a transverse circle, turning the M2 brane into a D2 brane of type 2A string theory. When we do that, that circle radius becomes the 2A string coupling that interpolates between D2 and M2 pictures. And the D2 Higgs branch metric is independent of that string coupling by a non-renormalization theorem of this amount of supersymmetry. So the Higgs branch metric of the D2 theory will give us the desired K3 metric. Okay, this is actually an analog of 3D mirror symmetry, which is a field theory duality, but for basically for little string theories, which give the compact moduli space. Now, very nicely, that Higgs branch metric that we can obtain classically by hyperkähler quotient in this picture should also encode an infinite number of BPS state counts via the mirror map to the Coulomb branch picture, and some of that has been fleshed out. Okay, so how can we obtain a tractable formulation of the classical Higgs branch of a D2 on K3 to actually get formulas for the metric? So I'll go quickly through that. Okay, first of all, consider a D2 that probes an orbifold K3. Here's a very famous orbifold K3 T4 mod Z2. Okay, so for D branes on K3 orbifolds, or any orbifolds actually, there's a completely explicit formulation developed by, for instance, Douglas and Moore. Now, I'm not going to get, any credit for writing down the metric on an orbifold. We all know the metrics on orbifolds up to conical singularities. They're flat. But the important point is that this Douglas-Moore formalism gives you explicit field theory deformations that include the orbifold blow-up modes. And so if we can get an explicit enough formulation on the orbifold, we can blow it up and get an explicit formulation of smooth metrics in an expansion around the orbifold point. Okay, and in fact, you can show, and this is part of what Max and Arnav are doing, that determines the metric in a large swath of the moduli space. Okay, so let's work up to the relevant theory in little steps. So here's the first example. Let's just study ND2s, not transverse to K3, but just to C2. What could be easier? So the D2s in flat space have, at low energies, maximal supersymmetry, 3D n equals 8. There are, naturally in some picture 8 scalars, but it's more natural to view them as 7 scalars in a photon. We'll view, the dual photon and its real scalar partner as things that we just set to 0. Okay, and we'll take the other 3 complex scalars and view them as adjoints of a 3D n equals 4 vector multiplet, because an n equals 8 theory certainly has n equals 4. So we could sort of say, by choosing non-covariantly an n equals 4, one of those lies in the n equals 4 vector multiplet, and the other 2 are hypers. Okay, and then there's a superpotential guaranteed by the supersymmetry, which is just this sort of commutator superpotential of that much supersymmetry. You multiply the adjoint by the commutator of the hypers. Okay, the equations that follow from that superpotential tell you that U and V commute, and the D-flatness condition that comes from the fact that they're in the adjoint tells you that UU dagger plus VV dagger is 0. So the moduli space spanned by those hypermultiplets is the solution of those equations' mod gauge transformations. Solutions of those equations are diagonal U and V up to the action of a permutation group, which is the Weil group of the gauge symmetry. It's not entirely trivial to prove that. It's proved in our paper. I mean, it's not a deep fact, but it's harder to prove than you'd guess. Okay, example 2. Let's work up in steps. Consider the quotient C2 mod Z2, because we're going to have to do K3 orbifolds. So now, okay, to get the Z2, we're going to start with a covering theory that has a D2 and its Z2 image on the C2. Okay, this is just the n equals 2 case of this example, 2 D2s. Okay, and we'll do a Z2 orbifold action. So the orbifold action, we think of it as acting geometrically on the space, but it also acts on the d-branes and on their Chan-Payton factors. We'll take it to act by conjugation by the sigma z matrix. You normally think of permutation as acting by sigma x, that is 0, 1, 1, 0 permutes 2 points. But it's more natural to choose sigma z following Douglas and Moore. So we do that here. And so we impose these projections on U and V and on the gauge transformations that survive in the projected theory. And we obtain a general parametrization in terms of charged fields U plus V plus, U minus V minus, and a subset of the gauge. The superpotential constraint that comes from the superpotential that descends to the orbifold, so that'll be like the adjoint phi times U plus V minus V plus, minus V minus V plus, tells us that up to a constant, U plus V plus is proportional to U minus V minus. That's just solving the superpotential constraint. The constant we'll call lambda. D flatness, that tells us that the norm of U plus squared plus V plus squared is equal to the norm of U minus squared plus V minus squared, tells us that the normal lambda is 1. And then using gauge freedom says that we can rotate lambda to just be 1. If you stare at the formula for U plus and U minus and V plus and V minus, you see lambda transforms with charge 2. So setting lambda to 1 leaves a Z2 unbroken, and that Z2 precisely takes UV to minus U minus V. So we obtain, as the moduli space of this theory, a copy of C2 mod Z2, as promised. Okay, now we need to make compact examples. We're working up in little steps. So let's first make copies of the 4 torus. That's the next easiest example. To do this, we use technology developed by Waddy Taylor in the mid-90s, he's interested in studying matrix theory. So we'll realize T4 is our 4-model lattice lambda, the 4-dimensional lattice. If you have k branes on T4, okay, whose moduli space would be sim k T4, they lift to an infinite number on the covering space, sort of k in each region, separated by shifts in the lattice lambda. So the matter fields that stretch from branes to the branes in different copies of the covering space, UIM, JN, with I and J going from 1 to K being gauge matrix, sort of gauge matrix indices, and M and N lying in the lattice, span this sort of infinite dimensional, really complicated matter sector, most of which are extremely massive matter fields because they're stretching between distant points separated by big lattice vectors and lambda. Okay, so this is a lot of indices. I'm going to leave the UK gauge indices implicit and label the fields as just UMN, where M and N label the lattice. Okay, so that the different M's and N's are branes in different lattice chambers. Okay, so then the orbifold projections yield some various facts. One is if we just shift the lattice locations M and N by lattice vectors, if M and N are different, then nothing interesting happens. That's just a shift in the orbifold group. If M and N are diagonal, then that's actually moving branes to a different region in the cover, and so we shift by LU times the identity, and same with the V's. Here the L's are just sort of 2 complex coordinates that parameterize the torus. And given these sort of shift symmetries in the orbifold group, it turns out that only the UNs, i.e. U0n, and the VNs, V0n, are independent. All other examples of sort of stretched strings between pairs of branes in different copies of the fundamental domain can be obtained by shifts. Okay. So in particular, UMN is equal to UN minus M if M is not equal to N, and UNN, the diagonals, are just given by the 0 mode plus a lattice shift. Now, how would you derive the low energy theory in this picture? Well, all the massive modes with n greater than 0, they come from strings that stretch between a brane in the 0th region and the nth region, separated by a lattice vector. They're massive, you'd integrate them out. You'd expect to get an interesting metric, but with this much supersymmetry, you don't. In fact, you just get the metric on a torus. But in the analogous K3 case, which we're about to discuss quickly, the analysis of the blown up orbifold just involves integrating out the massive modes, the analogs of the UNs here, to get the low energy action for the 0 modes. Okay, so finally, let's do the Kummer K3 orbifold. I have 2 slides left, so I'll finish hopefully 1 minute late at most. So let's repeat the previous construction. There are 2 simple modifications. We replace the 4 torus with its Z2 quotient. And so now, instead of studying just a U infinity to the 4th gauge theory, as we did in Taylor's construction, we'll study U 2 times infinity to the 4th. With projections, again, now the Z2 projections are again given by conjugation by sigma Z, just as we saw when studying C2 mod Z2. But again, there are UNs and VNs, just as there were in the torus orbifold of Taylor, because we can study strings that stretch from a brane to an image brane separated from it by a lattice vector that compactifies the space. Okay, so this resulting U2 infinity to the fourth theory, okay, has 58 parameters that come from 48 phi Heliopoulos parameters arising at the singularities, the Z2 fixed points, and then 10 metric parameters for the covering 4 torus. If we integrate out the massive UNs and VNs in this case, okay, in the presence of the non-zero Fi terms, and write the kinetic terms for the remaining low energy scalars, that's an expansion for the K3 metric. We checked at lowest non-trivial order in the blowout modes that the resulting metric is Ritchie flat. You can check to higher orders to your heart's content. At high enough orders, you'll start to encounter physical singularities that can be regularized in the normal way in physics. But as analysts, Max and Arnav are trying to make a mathematical theory of that. We checked that a suitable Poisson summation of the resulting formulas yields a match to the Coulomb branch picture and also allows you to read off the BPS spectrum of certain gauge theories that arise in the Coulomb branch picture. Okay. And Tripathi and Zimmet did further work and reproduced and predicted new BPS counts of other field theories using the same idea. So I'm out of time. Let me just say that much further work, both to formulate expansions around other loci and to prove convergence results about the expansions, is underway by Max and Arnav, and also by Laura Fredrickson and Rafe Mazzeo and other experts from the geometric analysis community. The resulting BPS invariants in the Coulomb branch picture have interpretations in enumerative geometry as disk counts. So there are going to be predictions for algebraic geometry that come out of this. There are some already that are related to these Minahan-Nemeshansky BPS counts. And that's all I had to say. So thanks for your attention. Let me unshare.
Oh, thank you for the great talk. Let's thank Shamit. And are there any questions?
Hi, Shamit. This is George. It was a very nice talk. Wonderful work. So can you comment a little bit on the physics side, what you would like to do with this K3 metrics?
Yeah, to tell you the truth, George, I did this because it's technically sweet. I actually don't know what physics questions you need explicit formulas for the metric for. I think probably the best answer to that question is that, and this will be a little bit odd as an answer, but in 4D n = 2 field theory, morally you should be able to know the metric. And yeah. K3 is arising here as sort of a metric of a 4D n = 2 or 3D n = 4 theory. So it felt like you should be able to get it. The analogous question for Calabi-Yau threefolds is sort of trying to figure out something more like the metric on a moduli space of an n = 1 field theory.
Right.
And there, we don't quite yet know morally why you should be able to get that information, right? It seems like it should be hard to get. So really, my own view of this as a physicist is I was interested as a warm-up for the next problem to see if it suggests sweet technical techniques. But also, I think as sort of somebody who does mathematical physics, the thing that I enjoy about this is the interplay between the two sides. So, okay, my personal answer is I couldn't care less about the metric, but the fact that a classical hyperkähler quotient construction determines these infinite sets of BPS sums and disk instantons, I find really cool. And in fact, it's sort of, it's an analog for the actual Calabi-Yau metric of what we do in moduli space all the time. We use mirror symmetry to solve for the moduli space metric of Calabi-Yau threefolds. Here we're using mirror symmetry to solve for the actual Calabi-Yau metric in some simpler case. So it's another one of these analogies between different quantization pictures in string duality, if you want.
Okay.
I don't know if that really answers your question or not, but that's my answer.
Okay, well, it's a good answer. Thanks. It was fun. That's great.
Any other questions? So maybe I have one actually. So and maybe I'm misunderstanding. So you write down the metric as an expansion away from certain loci in moduli space. Is that correct?
That is correct.
Right. So this isn't giving you the metric as a function of moduli all over the moduli space or anything like that.
I think the claim is that
start from some special.
I think the claim is that the expansions are sufficiently convergent that you can get a formula for I think Max and Arnav will claim you can actually get the full metric on moduli space everywhere. what we showed in our paper, at least at a physical level, is that you could get the metrics on a 25-dimensional subspace of the moduli space of K3 surfaces. So the expansions are sufficient to determine the metric. Think of special geometry. And again, I was telling George, there's an analogy to what we do in moduli space all the time. So mirror symmetry gives a convergent expansion above a certain value of the size in standard mirror symmetry, and then you analytically continue the formula. So I think you should imagine this is very similar, where you'll sort of get expansion somewhere, and then you should analytically continue.
Right. Okay. Thanks. Well, I'm sure if there are other questions, people can contact you offline. And if not, let's thank him once more.